Hello everyone, my name is Sahil, and today I'll be discussing my report on Lab 1 from Physics 2211 called Constant Velocity. So, as a brief introduction, the purpose of this lab is to determine the main difference between the real world and the computational world in terms of how an object is moving in a constant state. So, what this means is basically an object is moving with a constant velocity. Net force on the ball is zero, so there is no other force being applied on the ball once it's initially been pushed, and the ball will keep moving and won't stop because that just follows Newton's first law of motion, which an object staying in motion will keep staying in motion until another outside force will act on it, which could be like it to stop it or to make it move in another direction. So here we have our experiment. It is set up on a billiards table using a billiards ball as our object. It will initially be pushed with a certain amount of force, and it will move in the negative x direction, and it will keep moving until it is stopped by the other end of the table. So this is our experimental model, and this is our real world model, where we see the object moving and being affected by certain forces, as you can see on the right as a preview. In comparison, we have our computational model, where we use a computer system to generate the motion of a certain object. So here we have a ball, and the ball has a certain mass. To determine how fast this ball is going to move in comparison to the real world model, we use the first couple of frames of the real world billiards ball moving as our initial velocity. And with these frames, we got that the ball's initial velocity will be negative 0.389 meters per second. With this, we can calculate how constantly the ball is moving in this computational model. So we use these equations and manipulate them. So we have the ball's velocity, and we add delta t times f net divided by ball dot m. That is basically a manipulation of the f equals ma equation, where a is split into v and t, and then we use the v as our additional step to add to the original velocity. And then finally, we also update the position as well using the velocity equation. So velocity equals distance times time, and then we manipulate it, and then that is updated as well. All the formulas are provided, and the link to the code is also provided here. Now we can compare the two graphs of how these two models compare. So first off, we have a real world model, and then we have our computational model. As you can see at the beginning, they are very similar. It's pretty much a straight line. Towards the end, you can see that the observed model, which is the real world model, tapers off at the end. Why is this the case? Well, there is definitely a force being applied on it, and that is the force of friction. That is something the real world has to take into account of, because we don't live in a computer-generated world, and that in itself shows that there is something applying a force to it, that curve. So that is one main difference. There's also several sources of error. As you can see, there are bumps in the observed model, which indicate that the surface that I push the ball on is not entirely even, and the initial horizontal line at the top of the observed model means that there was some time delay in pushing the ball itself. So there are some sources of error to take into account here, but the main difference is the curve at the end. So that is the main difference, the force of friction being applied. Therefore, there is no constant velocity in the real world. There will be a force of friction that stops the ball from moving in a constant way. If we were to orient the axes, the force of friction would still be there. It would just be shown in the other direction. So instead of moving in the negative x direction, the ball would be moving in the positive x direction, but it would still be slowing down as the force of friction is being applied on the ball. What does it mean if the net force is zero? Well, the net force is not zero. in this sense, because there will always be a force of friction. We could do many things like manipulate the coefficient of friction, we could put it on smoother surfaces, but all of these still have a force of friction that is still applied on the ball regardless of how little it is. So that is the main conclusion from this experiment, that regardless of type of surface or the location, there will be a force of friction in the real world that the computational model cannot predict. So thank you.